my lecture today. Of course, we started the function of random variable yesterday. We're going to continue from there. We got a lot to do today. And of course, I'll be focusing on method of transformation today. And I'm also going to walk you through several examples on how we can actually go from one to one and two to two variables. So the other time we started, situation where we got a random variable x, and we know the probability distribution for random variable x. It could be uh, discrete, it could be continuous, and of course we have a new random variable y that's a function of random variable x, and all what we are seeking to do is to derive the probability distribution of the new variable, and that's exactly what we've been doing. But what is going to make today's lecture to be kind of unique is that you're actually going to see an opportunity, how probability distributions are being derived from another probability distribution. So, which means if a particular random variable follow a particular distribution, and we define a new variable, that's a function of the old variable, a brand new probability distribution will come out of that. But before going into that, like I said, I'm going to be, because one of the most, or maybe useful method of, of doing that is a method of transformation. So that's why I'm actually going for that. Now, I first want to start with a discrete distribution. Okay, as you can see in theorem 7.1, okay, if x is a discrete random variable, and of course the probability for that is f of s, and if we define a new variable y, which is a function of u, okay, and that we define what I call a one-to-one, one-to-one transformation between the values of x and y. Now, if I'm seeking to get the probability, a new function, the probability of y, that's a new variable, I'm actually going to have this. Now, I'm going to walk you through an example right now. Okay, if you look at example 7.1, you have a random variable, okay, that have this probability distribution. Take a look at that. S start from 1, okay, to infinity. That's a geometric distribution. Okay, S is a discrete random variable that follows geometric distribution. Now, we now want to find the probability distribution of a random variable y, which is equal to s squared. And don't forget, S follow a geometrical distribution. So if x follow a geometric distribution, okay, when I transform x, okay, the new distribution is not likely going to be a geometric. It's going to be something else. And that's what we want to do now. Now, by method of transformation, all we just need to do is, whenever you are dealing with the discrete distribution, okay, you're giving this guy here, you need to find the inverse of that, which is going to give me that, right? We shall solve it for x. I'm actually going to have a square root of y, okay? Now, if I have a square root of y, then what I'm just going to do, I'm going to come back into the distribution. Wherever I see s, I'm going to plug in square root of y, and that's exactly what I've done here. And when I plug in square root of y, I'm no longer going to use this state space, okay? Don't forget, where s is, the state space for s is 1, 2, 3, and don't forget, for y, it's going to be s squared. So which means I need to start squaring that. That was why you get that, 149. Now, if you want to handle, if the probability distribution is discrete, okay, and you want to do a transformation that has to do with one-to-one, it's very easy. That's how we do it. Okay. Now, you know what I want to do now? I'm still. I want to go into situation where I want to go from 2 to 2. I got x1, x2 that are discrete random variable, and they have their own probability distributions. And of course, I have a new variable y. Y1 is a function of x1 and x2, and y2 also a function of x1 and x2. And what I'm seeking to get? Okay, I may want to get the distribution of y1 and y2. Okay, now if I want to get distribution of y1 and y2, I need to first. What is my y1? This is my y1 is a function of x1, 1, 2, and y2 is a function of that. What I'm going to do is to find the inverse. Now, how am I going to find the inverse? I'm actually going to solve for x1. I'm going to solve for x2. That x1 is going to be a function of y1, y2. X2 here is also going to be a function of y1, y2, which is what I have here. Take a look at this. That is after solving for x1. X1 is going to be a function of y1, y2, and x2 also going to be a function of y1, y2. And if I actually want to get the distribution of y1, y2, all what I just need to do is I need a distribution of x1, x2. And wherever I see x1, I'm going to plug in this. Wherever I see x2, I'm going to plug in that. Then I'm going to have this. Okay, now I'm going to give you an example right now before I make use of the board. Now, let x1 and x2 be two independent random samples. X1 follow Poisson distribution. X2 also follow Poisson distribution. You know, the parameter for the Poisson distribution for x1 is mu1. The parameter for x2 is mu2. And you know what they wanted to find? They wanted to find the distribution of y1 equal to the sum of x1 plus x2. Okay, now let me tell you this. I need you to pay attention now. Okay, now I want to go from 2 variables to 1. That's not possible. Please, I need you to pay attention. I want to go from x1, x2 to y1. That's not possible. You know what I'm going to do? I'm going to create an artificial variable, y2. Because I can only go from y2 to 2 variable to 2 variable. Now, I can call that y2 to be s2, to be this. Do you know why I just created this guy? So that I'm actually going to have 2 variables to 2 variables. It's just like maybe my wife is not around and somebody invites a couple to a party and a couple must come to a party and my wife is not around. I can ask my daughter to follow me to go and act as my wife. But the moment we leave the party, my daughter is no longer my wife. So what I'm going to do here, introducing this guy, is just for us to be able to aid the transformation. At the end of the day, we're still going to have a way to marginalize this guy out. Okay, now what I'm trying to say, the very next thing you're going to do, because you've been told here that x1 and x2 are independent, okay, what you need to first do is this. F of x1, for my x2 is going to be the product of that, because you've been told the old variables, x1 and x2, they are independent. Now, you're going to have this. Now, what is f of x1? You've been told it's Poisson. That's why you have this guy. And they told you it's Poisson with a parameter mu1, which is this guy. Then x2 is a Poisson with parameter mu2, which is this guy. Multiply them, mathematically speaking, you're actually going to have this guy. Now, what you have now is the joint of the old variables. Joint for the old variables, x1 and x2. Okay, now after getting that, don't forget, you know where we're going? We want to go to the joint for the new variables, y1, y2. Now, what we're going to do, we need to solve first, find the inverses. There's going to be two inverses. You know what I'm going to do? Right here, I need to solve for x1. Okay? And, of course, automatically here, okay, x2 is going to be y2, which is this guy here. And x1 is going to be that. Is there any question on now? What I'm trying to tell you now, my inverses is this guy here. These are my inverses. Express old variable in terms of the new variables. I've expressed x1 in terms of the new variable, s2 in terms of the new variables. Now, what I'm going to do, in the joint here, in the joint, wherever I see x1 and s2, I'm going to plug in these guys. And that was why you got this guy here. Now, what are you having now? That's a function of the new variables y1, y2. There's no old variable anymore. Take a look at that. But what are you looking for? Don't forget, you are looking for the distribution, the way you're looking for g of y1. Okay? But that would be super cool because I can, when I get a joint, gy1, y2, I can get g of y1. Don't forget, when I'm working with discrete, I will need to come here and sum this over the range of the variable I'm not interested in. Does that make sense? So, which actually means if I want a g of y1 now, I'm actually going to have, I'm going to sum this y2 over g y1, y2. Okay? And that is what I'm going to do now. So, I have a joint, you know. Right now, it's like my daughter and I, we are at the party now. Okay? But after the party, what is going to happen? I'm going to go back to my g of y1. Okay, which means I'm actually going to, sum my daughter out, which is going to be what I'm doing here. Take a look at this. Do you see that guy? I want to get h of y1. Okay, now I'm going to sum y2 over the range of the variable I'm not interested in, which is going to be this guy. Take a look at that. Now, every other thing that I'm doing here is just going to be a mathematical, modifying that, and at the end of the day, I got this result. Now, what is it telling me? Do you know what it's telling me? If x follow poi with parameter, if x1 follow poi with parameter mu1, and s2 follow poi with parameter mu2, okay, now what I'm trying to tell you now, if y1 is x1 plus x2, what I mean is going to follow poi with parameter mu1 plus mu2. Take a look at this. If the g of x1 is, if you take a look at it, it's exponential raised to the power mu1 raised to the power x1 over x1 factorial. G of x2 is this, okay, mu2 raised to the power that over s2 factorial. If you compare this and this with this, do you know what is replacing the mean here? The mean is what? Mu1 plus mu2. Here, the mu is what? Mu1 for x1, mu2 for x2. So the distribution for addition now, adding x1 to x2, is actually what you see here. Now, how are you going to do this? If you want to look at the pattern, what about this guy? If I'm working with this for Poisson, okay, I'm afraid I'm actually going to have mu1 plus mu2 plus mu3. Does that make sense? Okay, that is how that goes. Now, I'm going back to continuous. I walked you through the continuous yesterday. Okay, now let me quickly see what I think I have a lot of examples that I put here. This is for, okay, let me quickly come to, let me see, the same thing here. Okay, if I want to do this now, okay, going by, this is for the way we did continuous is different. Okay, for continuous, after solving for inverse, I will need a Jacobian. Okay, so for this particular question now, where you have f of s equal 2 into 1 minus x, and it's 0 like that, and of course y equal to s squared. So here you need to first find that, right? S equal to that, which is y raised to power half. Okay, for continuous we need Jacobian. For discrete we don't need Jacobian. Now right now the Jacobian is going to be the x dy. Okay, the x dy is going to be half minus half, which is this Jacobian. The absolute value of the Jacobian is still going to be this. Okay, now if I want to write my g of y now, okay, it's going to be f into you know, x a function of y multiplied by Jacobian. So which is going to be, wherever I see x, I'm actually plugging that. So it's going to be this 1 minus square root of y, okay, multiplied by 1 over that. Do you see that? So that is the way that guy is actually going to go. But you know what? Okay, the way we actually approach that of the continuous is from the way we approach the discrete. Now, before I go into take a look at this, the application in physics and engineering, I wanted to pay attention and take a look at what I have right now.